So if we are given the graph of a polynomial function, like this one, and some additional information, so suppose the graph of the polynomial has the minimum possible degree, so degree is as small as it could possibly be, and that the leading coefficient is 1 or -1, here's the information we can sort of pull out of that. So notice the graph is scaled kind of weird. The y-axis is really zoomed out, but the x-axis is sort of more along the lines of what we're used to. But the things that we can do for starters would be to count things like turning points, 1, 2, 3, 4. Just make some notes on here for 4 turning points. There are 1, 2, 3 zeros or x-intercepts. And the other thing that we may want to look at, or sorry, not may, the other thing we want to look at would be the end behavior. So as usual, I'll just kind of draw some little arrows for what the ends do. Okay, now what these things tell me about the degree and I'll start with the end behavior. Since they point in opposite directions, the degree has to be odd. Four turning points tells me that the degree is at least 5. So number of turning points plus 1 is the smallest the degree could possibly be. Or to say that the other way, if we know the degree, then the maximum number of turning points is 1 smaller. So if I know that there are 4 turning points, degree can be no smaller than 5. And 3 x-intercepts means the degree has to be at least 3. Those match. Or the degree is larger than the number of intercepts. So taking all this information together, the smallest the degree could possibly be is greater than or equal to 5, but also greater than or equal to 3, which becomes irrelevant because 5 is bigger, right? We have to have all of these things true at the same time, and odd. So the minimum possible degree would again be at least 5 and also odd. Something that's at least 5 and also odd is 5. So if the degree is as small as possible, then we can say here that the degree is 5. The leading coefficient, the thing to pay attention to here is the fact that the graph eventually, sort of the last time we see it as it's like sort of exiting what's visible here, is pointing down in the direction of negative infinity. That means that the leading coefficient must be negative. And the problem tells us that we can assume that it's either +1 or -1. So really all we're doing is trying to figure out the sign. This has got to be negative. Again, that's because this end is pointing down into the negative direction. Okay, and then identifying the zeros and their multiplicities. So let me just erase some of this stuff so we can start over fresh. Zeros are x-intercepts. There are x-intercepts here, here, and here. So the actual zeros themselves are -5, 2, and 4. Then to figure out the multiplicities, we want to look at what happens nearby. So here, our function is decreasing as it heads towards this intercept, but then at -5, we get the function turning around. So there's a turning point at that x-intercept where it intersects the x-axis. If you want to think about that, as like a local sort of end behavior thing, both those are pointing the same direction. So anytime we see something sort of bouncing off the axis like that, that means the multiplicity is even. And if we're assuming it's as small as possible, that would mean 2. Here at x equals 2, I see the graph just sort of cross straight through the axis. That means the multiplicity is 1. And then here again at 4, I've got the graph sort of bouncing off. I didn't draw this. Okay, now they all match. Sort of bouncing off the axis here again, which again tells me the multiplicity is even. I'm assuming it's as small as possible, so 2 then. Okay, and then having all that information, we can put this together and write down a factored form for the function that this came from. Again, we're assuming, because the problem says we can, that pretty much what you see is what you get. Like this is actually what it appears to be, and it is. That's why when I made the graph, I had to stretch the scale kind of funny. But notice we haven't really paid any attention to the scale on the y-axis at all. So for all I care, that doesn't really need to be there. The only y value I actually care about is 0, which is the x-axis. Okay, factored form. So every 0 corresponds to a factor. So if there's a 0 at -5, that means we get a factor that looks like x plus 5. The multiplicity being 2 means that that factor shows up twice, so it's squared. Okay, the next 0 that we have is 2, which would come from a factor that looks like x minus 2. Multiplicity 1, so I don't need to actually write that because exponent 1 we can, it's just implied if it's not there. And then 4 would come from a factor that looks like x minus 4. Again, that one's got multiplicity 2, so squared. And then because the leading coefficient's negative, I'm just going to throw a negative sign out in front of the whole thing. So that if I did the expansion here, I would end up with negative x squared times x squared. So the leading term would be negative x to the 5th, which matches all the other stuff that we've seen. And then, of course, you can check if you graph this. Again, you're probably going to need to fiddle around with the window settings a little bit to get a good picture of it, but we could graph that and verify that it matches what we have. Okay, well, that's information we can get from a graph about the polynomial that it came from. I hope that is helpful.